Hello everyone, I'm Akiva. I've done this talk twice before, so I apologise in advance if you've seen this before. I was a maths teacher for 40 years. I'm retired now. I taught in secondary model schools, comprehensives, further education colleges and universities. And usually when I tell people I was a maths teacher, not always, but most of the time, the reaction I get is, oh no, not maths, no. Oh, I was always hopeless at maths, which is a shame. I mean, I do appreciate that a lot of people do have difficulty with maths, but what does get up my nose a bit sometimes when somebody sort of boasts of it, say, oh, I was always hopeless at maths. I was much more on the artistic, creative side. And they seem pleased, it's great to be bad at maths, because it proves that you're creative and artistic, which is a terrible position to take, really. Particularly if it rubs off on kids. Anyway, from that you can gather that I love maths, and I'm particularly interested in the history and philosophy of maths. And I'm particularly interested in this guy Euclid. Now Euclid was an ancient Greek mathematician. He flourished around 300 BC in Alexandria. He wrote a book called The Elements. Now what he did something really sort of incredible. He brought together all the maths that was known in his time, which was mainly geometry, arithmetic as well of course, but not algebra. That wasn't invented till about 1,000 years later with the Arabic civilization. So he wrote this book called The Elements, and it contained 13 books which proved 465 propositions in geometry, all the things that you learn about in school, about triangles and squares and circles and things. Once proved, they're called theorems. So he starts off calling it a proposition, then he proves it with absolute certainty, and then you're entitled to call it a theorem. And he proved all of it. He proved all these 465 propositions in maths. For example, the 47th theorem that he proved, so he didn't actually invent these theorems, but he proved them. He collected them all together and proved them all. The 47th theorem is Pythagoras' theorem. Do you remember this from school? If you have a right angled triangle, is that right? From this angle, right. If you draw a square on each of the three sides, right, then the biggest square, the red square, is equal to the other two squares. The area of the red square is equal to the areas of the other two squares added up. This was really, really important and useful in maths. But yes, it was. He started off with 23 definitions of what's the definition of a point, what's a line, triangle, a circle, etc., etc. 23 definitions of those. And then he had what he called 5 common notions, which are obvious truths, but for general truths, not just for geometry. What were these? Right, the first one. Things which are equal to the same thing are equal to each other. What does that mean? Well, if Tim's got the same amount of money as Piano Man Dan, and I've got the same amount of money as Piano Man Dan, then Tim and I must have the same amount of money. That's what it means. Well, he's got much more than me. If equals be added to equals, the wholes are equal. So if Tim and I both got £10, and Piano Man Dan gives us both £2, we're still equal. Similarly, if equals are subtracted from equals. So if we've got £10 each, and Piano Man Dan takes away £2, we're still equal. Things which coincide with one another are equal to one another. Well, this is like if you've got one triangle that fits exactly on another triangle, well, they're the same triangle. So it's pretty obvious. Hardly needs saying, really, but... And the whole is greater than the part. Well, a whole cake is bigger than a slice. So these are really obvious, self-evident truths. Now, he also stated 5 postulates or axioms which related specifically to geometry. Now, an axiom, what is an axiom? An axiom is a truth that is so obviously true, so simple, so self-evident, that it doesn't need to be proved. Because if you're going to prove things, you've got to start from somewhere. You can't prove everything, you've got to start somewhere that doesn't need proof. So an axiom is something that is really, really so simple and evident you don't need to prove it. Now, I can't overemphasise the importance and the effect that Euclid's work had. For thousands of years it was held up to be the most supreme piece of work, because you start off with things that nobody can argue about, it's obviously true, and then you prove logically with absolute certainty all the stuff that comes next. So it's regarded like a perfect piece of work, and everybody sort of looked up to it and tried to copy it. I mean, non-religious people would swear on Euclid's books rather than on the Bible, because it contained absolute truth. For example, the philosopher Baruch Spinoza, he wrote a book called Ethics, but its full title was Ethics Proved in Geometrical Order. Now, there was no geometry in it, book on ethics, but he started off with some axioms, self-evident truths, simple truths that nobody could argue about, and then he deduced logically things that came afterwards. Look at this other example. You see how it spread through all types of culture throughout the world. Look at this example. We hold these truths to be self-evident, that all men are created equal, they are endowed by the Creator with certain unalienable rights, and among these are life, liberty, and the pursuit of happiness. It's the American Declaration of Independence. Starts off, we hold these truths to be self-evident. They were specifically, deliberately following Euclid's method. Right, what were his 5 axioms? Right, the first one, to draw a line from any point to any point. Right, so if you've got 2 points, you can draw a line joining them. Number 2, to produce a line continuously. If you've got a line, you can make it longer. Obviously true. Hardly going to say that obviously, but he needed these axioms. To construct a circle with any centre and radius. So if you're given a specific centre and specific length of radius, that will allow you to know how to draw that circle. That all right angles are equal to one another. Well, again, hardly worth saying, obviously. The 2 right angles are the same, they're both right angles. But you can see how self-evident and obvious and simple these are. Now, the 5th axiom. This is what caused all the trouble. Now, don't run out screaming when I show you this. This 5th axiom. That if a line falling on 2 lines makes the interior angles on the same side together less than 2 right angles, 2 lines, if produced differently, each on that side, on which are the angles together less than 2 right angles. So, what do you think? I'm sure when you read this, your reaction was the same as mine. What the fuck is that? I mean, do you understand it? I don't understand it at all. The people were very unhappy with it. Because what is an axiom? An axiom is a truth that's so simple, so it's true, so it doesn't need to prove. Well, that's not simple. You barely understand what it's saying. What is it saying? Like, if you've got 2 lines and you draw a line going across it, it will make angles. Right? You've got these red angles above the line, you've got these green angles below the line. What he's saying is, if you draw those black lines longer and longer, they will meet on the side where the red angles are. They won't meet on the other side. It is sort of, it's when it's explained like that. But this is equivalent, logically, mathematically, to this. If the angles, all four angles are the same, they're not going to meet above the line, they're not going to meet below the line either. Right? Now, people were very unhappy about this axiom because it wasn't obvious and it was very complicated. So, mathematicians, for hundreds of years, they tried to get around it. First of all, they tried to see if they could prove that axiom from the other axioms. And if you could prove it, you don't need to call it an axiom, because you can prove it. You don't have to just believe it without proof. And they found they couldn't do that. Then they tried to do without the axiom, and see if they could have all the other theorems that came afterwards, but they found they couldn't do that either. So they thought what they were trying to do, they were trying to prove that axiom by a method called reductio ad absurdum, a sort of method in logic and philosophy, reduction to absurdity. What does this mean? If you want to prove something, what you do using this method, if you want to prove something, you assume the opposite. You assume it's not true, and show that that leads to a contradiction, therefore you prove what you wanted to prove. Right? Let me explain that here. If you want to prove something's true, assume it's not true, show that that assumption leads to nonsense, therefore that way you prove what you wanted to prove. I want to give you an example of reductio ad absurdum using prime numbers. Do you remember what prime numbers are? Prime number can only be divided exactly by 1 and itself. Right, these are the first few prime numbers. 2, 3, 5, 7, not 9, because that could be 3 times 3. 11, 13, not 15, that could be 3 times 5. 17, 19, not 21, that could be 3 times 7. 23, not 25, that could be 5 times 5. Not 27, that could be 3 times 9. 29, etc., etc., etc. Right? Now, with prime numbers, the higher up you go into the millions and billions and trillions, prime numbers become very rare. You go for millions and millions without finding the next prime number. So people wondered, do prime numbers go on forever? Or can you get a prime number that is so big, so huge, that there isn't another one after that? The prime numbers come to an end. You could have a final biggest prime number. Now, with reductio ad absurdum, you can prove that prime numbers go on forever. Let's see how that's done. To prove by reductio ad absurdum that prime numbers go on forever, that there isn't a biggest prime number. This is what we're going to prove. So, how do we prove it? We want to prove there isn't, so we assume opposite. We assume there is a biggest prime number. Right? Assume the opposite. Assume that there is a biggest prime number. Call this number P. Right? So P is the biggest prime number you can get. There is another one afterwards. Right, now theoretically, we can theoretically construct a new number. So what you do is you multiply theoretically all the prime numbers that exist up to including P. So, like this, 2 times 3 times 5, times P. So this is all the prime numbers multiplied together. Now let's see what happens when you add 1 to this. You've got all those prime numbers multiplied together plus 1. Now 2 goes into it times all the others, remainder 1. 3 goes into it times all the others, remainder 1. Each of them goes into it times all the others, remainder 1. So nothing goes into it exactly. So this must be a prime number. And it's obviously bigger than P. So we've reached a contradiction. P is the biggest prime number, P is not the biggest prime number. Right? Which is rubbish, it's nonsense. It's a contradiction. So it can't be true. So our initial assumption must be true, that you can't have the biggest prime number. So that's the method, the reductio ad absurdum. Now they wanted to use this method to prove Euclid's fifth axiom. So they assume that these lines can meet. Right? They want to prove that these lines don't meet, to prove the axiom's right. So the reductio ad absurdum assume the opposite, assume that those lines will meet. And hopefully we get a contradiction. But it doesn't, you don't get a contradiction. And how do we know that you don't get a contradiction? Because we use what's called mathematical modelling. We find a model for it, which is this. Can you see that faint green line? Now, why would this prove that it's not a contradiction? Well, because contradictions can't actually exist, and yet this model, there is, it's existing. So, on this model, you've got two people, green person and blue person, they're starting off at the equator, and then walking northwards. They're both definitely right angles, but they will meet at the North Pole. Now, this looks like cheating, but it's not really. It's just, you need to just tweak your definition of a straight line. So, when these mathematicians, there were two mathematicians that came across this independently. One was called Lobii, one was called Lobachevsky. And first of all, they thought, oh my God, what have we done? We can't fuck around with Euclid. Euclid's the man. We can't do anything that goes against Euclid. He's God, practically. You know, all the other mathematicians would laugh at us. And they did. Other mathematicians did laugh at them. So, but you're talking rubbish. You can't go against Euclid. But over the years, it was realised that they've hit onto something. That you could have alternative geometries, non-Euclidean geometries. For example, air traffic controllers would use this geometry, not Euclid. Space travel would use this sort of geometry. And it also got mathematicians to realise that you could have any set of axioms, as long as they're self-consistent, as long as they don't involve a contradiction amongst themselves, you could have any set of axioms and develop new systems of mathematics, not just in geometry. And it opens up a whole new thinking about what the foundations of maths were. So although Euclid is still sort of revered as, you know, the greatest, it freed mathematicians from the shackles of Euclid. It allowed them the freedom to develop in new directions. Anyway, that's it. So we found this a bit interesting.